Good morning, everyone. Is this working? You can hear me on the microphone. Great. It is really a pleasure. Can you guys hear me? Yeah, that's good. Okay. I know there's cheese balls. This is a really exciting aberration. Not only are we in a different room today, but there's cheese balls. So it's really exciting. No, yeah, we need a little bit more fat to carry us all the way to this faraway room. Well, thank you all for being here this morning. It is really a distinct pleasure to welcome Dr. Andrew Hoffman here for our seminar today. I met Andrew about 15 years ago, although obviously there's a lot of resonances between our science. We actually met singing in the same choir at St. Olaf College, where Andrew studied physics and mathematics. He graduated in 2016 with his bachelor's and then spent a year at the University of Copenhagen as a Fulbright scholar. Following that, he did his PhD at the University of Washington, where he graduated in 2023 and is currently a postdoctoral research fellow at Lamont Doherty Earth Observatory, where his work focuses on remote sensing of ice dynamics, radar imaging of englacial structure, and the use of geophysical observations for sea level rise impacts. In a couple of months, Dr. Hoffman will begin as an assistant professor at Rice University down the road, where he will lead the Oceans and Cryosphere group, developing new observational and modeling approaches to understanding how ice sheets, oceans, and coastal systems evolve in a changing climate. So without further ado, help me welcome Dr. Andrew Hoffman.
There we go. Okay, you can hear me now? Perfect. Okay, yeah, so as Ben said, I'm a radioglaciologist by training. And I think about ice sheet and ocean processes. The drone footage that you're seeing behind me is from East Greenland. So this is actually an interior location, so very far from the ocean. But this is kind of where I got my start in glaciology and where I'm going to be presenting radar data later in the talk. Other of important connection with East Grip in particular, which is in Northeast Greenland, is it's, again, as Ben said, kind of where I got my start in glaciology. So I'm going to talk a little bit later on about rover systems, but I started in glaciology kind of as a systems engineer designing a semi-autonomous rover to understand or profile englacial layers in the near surface as part of the Surface Science Consortium. And I'll highlight again too throughout the talk that a lot of the efforts that and the data that I'm going to present today wouldn't be possible without international collaboration with folks in Denmark and the support from Greenlandic technicians. So the work that I do in Antarctica and Greenland is motivated by what we know about sea level rise, but what we don't understand about ice sheet and ocean processes that contribute to glacier melt. So this is a familiar figure from the IPCC report. Shown here is the global mean sea level change relative to 1900. From 1950 to 2020 are observations, and then from 2020 onward are projections from the shared socioeconomic pathways. And what we find is that as you increase or emit more carbon in the atmosphere, you're going to get more sea level change. But climate modeling compared to ice sheet modeling is in its infancy. Or sorry, ice sheet modeling compared to climate modeling is in its infancy. And so there's processes that we don't completely understand. For instance, the grounded ice cliff failure or the retreat of ice sheets in connection to kind of their interior response. And when we kind of include that physics, our projections change dramatically. And kind of as an aside, it's also important to kind of rethink and imagine what each of these scenarios is actually like as like a world. And I like to appeal to climate fiction when I'm teaching classes on this kind of topic, because I have a really difficult time actually imagining the governance that's associated with each of the shared socioeconomic pathways. But we can appeal to books like The Water Knife or 40 Signs of Rain to understand kind of the choices that we make that are actually causing the emission scenarios that we're projecting. And I know I don't want to live in either of those worlds. So we can dive a little deeper into these curves. Here I'm showing projections again. The x-axis is time, on the y-axis for all these plots is meters of sea level change. And what we find is that across all of our simulations and projections, the largest source of uncertainty in our models comes from the large ice sheets, and particularly Antarctica. We also find that the rate of sea level is accelerating, especially up until 2100, and that after 2100, the dominant contribution to global sea level change is coming from ice sheets. So all of this is just motivation for understanding kind of, and in order to refine this uncertainty, we need to understand at the process level, the physical processes linking nutrition and cryosphere. So that's the goal of the research group that I'm hoping to start at Rice University. This is a schematic of an ice sheet. Flow is happening from this interior divide location out to an ice stream, an ice shelf margin. And my research group thinks about a broad array of questions to kind of achieve this goal of understanding uncertainty associated with ice sheet and ice shelf melt. We think about questions that are kind of ice sheet engineering questions, like how much and how fast will the West Antarctic ice sheet contribute to sea level in the next century? Process-driven questions, like what drives ice shelf melt? How does ice deform and fracture? How do glaciers slide? And then also questions that connect to other parts of the Earth climate system. So how does the solid Earth affect glacier flow? And then how have ice sheets and oceans changed over Earth's history? And we tackle these questions using a holistic approach that combines satellite geodesy and radar altimetry, ground-based and airborne geophysics, ocean hydrographic measurements, and then we kind of combine all these data, process data using objective methods, and then whenever possible, assimilate this information into models of ice sheet flow, but also ocean circulation. And so for this talk, I'm going to focus kind of on one component of my research group, which is a component that's focused on like radar observations and processing methodologies. So the first part of the talk is going to introduce a method called swath processing, where we're going to use a multi-element array to image internal structure and bed topography in 3 dimensions. The examples I'll pull from are mostly from Hercules Dome, on the East Antarctic margin, in kind of a configuration where we can understand potentially West Antarctic collapse. The second part of the talk will talk a little bit about multipass radar interferometry, and focus on data sets from Greenland that can be reprocessed to understand englacial deformation. And then the third part of the talk will focus on polarimetric radar observations and how these data can be used to understand weather patterns. A lot of the work that I'm going to show today wouldn't be possible without support across a bunch of different institutions. So most of these are shown here. And particularly has been a lot of leadership from the UTIG geophysics group. So I want to recognize that. And folks like Duncan Young and Don Blankenship, many others have been collecting data, Ginny as well, across all of these regions. And so it's really by combining these data and processing data in a unified frameworks that are supported by efforts like Open Polar Radar, where we can kind of develop or combine these different methods across both ice sheets. Okay, so the radar systems and the data that I'm going to talk about today are collected using platforms that can kind of be represented here. So shown is a trace that's being collected, or a profile that's being collected using an array. Located here is a radar computer, and that's where I'm currently programming the waveform that we're going to transmit. Or we're going to build instructions to then send to a digital system that's going to generate, amplify, and transmit that waveform down to an antenna array located here. And so with radar measurements, there's really 2 kind of time scales. There's a fast time scale associated with the propagation of this wave into the subsurface, and then a slow time scale that's kind of demonstrated here, where we're driving or flying at the surface. So now I'm going to show a simulation of that fast time scale. This is happening at a rate of about 14 microseconds. Is kind of the repeat cycle of this kind of measurement that we're making. What I'm showing is an EM simulation of a radar wave that's propagating from the surface at a transmit location. And there's all these reflections that are happening off of internal layers. These are conductivity and dielectric permittivity contrasts within the ice. And we see that there's reflections off of all of these internal layers, but then also a really large reflection that we see off of the bed. And all of this is being recorded at a receiver that's located at the same location. So on the x-axis here is power of the amplified signal as a function of two-way travel time, which we convert to depth. So this is kind of what's happening in all of the measurements that I'm going to be talking about today. If we combine all of those traces sequentially as a function of kind of a long track distance as we move along a profile, we can build these radargrams. And so these might be familiar to some of you if we've seen talks from Duncan or Don, where trace distance or trace number or distance is on the x-axis, and then two-way travel time is the y-axis. So these data have been used or combined to understand bed topography across Greenland and Antarctica. So shown here is the Operation Icebridge archive and other data sets that were collected by UTIG, Lamont, the University of Washington, and the contiguous US is shown here for scale. And I looked this up yesterday. The University of Texas has collected just over 25% of the line kilometerage that's shown here. And so as an institution, UTIG is kind of, I think it's only AVI that's collected kind of this similar volume, and then CRESIS, the Center for Remote Sensing and Integrated Systems, but was the Center for Remote Sensing of ice sheets. So a lot of history and a lot of the data that I'm collecting extends from work that's been done here at UT. So the first method that I'm going to talk about, that's kind of building on this processing workflow that's analyzing or reconstructing bed topography in 2D profiles, is an extension of that method where we're going to image the ice sheet internal structure and bed topography in 3 dimensions. So shown here is a nadir-focused radargram where we're looking a long track. Again, distance is the x-axis, the y-axis is two-way travel time. But because we're transmitting and receiving using a multi-element array, we can reconstruct and geolocate energy that's coming from across track from beneath our antenna and receiver array. So we're using subtle changes in phase and range to reconstruct then the 3D backscatter as a function of distance along flow. So this is, I'll kind of talk a little bit about the method or the data structure itself. Instead of these 2D traces or the 2D profiles that we're using or building from 1D traces, here we're now building volumes from 2D surfaces. So I'll talk a little bit about some of the extensions that we can make or examples of interpretations we can make. The first is going to come from West Antarctica or the margins between kind of the West Antarctic ice sheet and the East Antarctic ice sheet at Hercules Dome. This is the site of a deep perspective deep ice core. I think 5 years ago, I said that in the next 5 years, we'll have ice from Hercules Dome that will reveal the collapsed configuration of waste. But that's, I think maybe in the next 5 years, we will have an ice core here. So the intention of the ice core, though, is to understand the configuration of the West Antarctic ice sheet during the last interglacial. So this is a simulation that's shown here from Dave Pollard and Rob DeConto, showing ice thickness for potentially a collapsed configuration of WAIS. And at Hercules Dome, we see that Hercules Dome there's thick ice present at Hercules Dome, so it preserves information about the climate during this period when the West Antarctic ice sheet could have been smaller. But it's close enough to potentially also be sensitive to changes in the oxygen isotope log as well. So the goal with the ice core is to drill a core that could potentially see how the surface has changed over here and measure that change as a function of depth at Herc Dome. So, and as part of a geophysics team that's citing the location for that core, our goals are kind of related. We're interested in what can the subglacial landscape at Hercules Dome tell us about glaciation. So this was done in collaboration with lots of folks, particularly though Nick Holshoe at Amherst College, Megan Mueller, who was at the University of Texas Austin and is now working between Austin and University of Arizona, and then Knut Christensen at the University of Washington. Lots of early career and folks who were graduate students working together at the University of Washington. So here I'm showing the existing coverage that was collected as part of the polar gap surveys at Hercules Dome in blue, and then in yellow are the new surveys. So our data are concentrated around this divide region. Flow at Hercules Dome is extremely slow, so there's a divide center. And ice here is, we drill ice cores where kind kind of the snow is being deposited and is just flowing vertically with depth. This is the radar system that we're using. So in this case, instead of just a single element, we're using 4 elements. And this is what allows us to image the internal structure and the bed topography in 3 dimensions. The digital system for this radar is actually located on top of this multi-element antenna array. And what we find at Hercules Dome from our ground-based surveys is evidence of an alpine valley landscape. So in background in panel A, I'm showing the bed machine profiles, or the bed machine topography, which is an interpolated product from all those kind of sparsely spaced line data. And then on top of that, I'm showing the 3D swath images that we generate using our multi-element array. And what we find is that there's evidence of large U-shaped valleys and then lineated features in areas where the current flow speeds of the ice sheet are less than a meter per year. This is just another figure that's giving or building kind of a sense of scale for this system. So we see evidence in nadir focus profiles of arêtes, subglacial lakes, hanging valleys, more troughs. And then here I'm showing in panel B a swath image of the bed, and then in panel C a LiDAR image of Half Dome. So the size and scale of these features is something like the Yosemite Valley. Because these data are inherently 2-dimensional in their structure, we can use the data or use different kinds of metrics to understand the character of roughness of the topography in this region. So in panel B, I'm showing the elevation anomaly for this region, which I'm going to call the highlands. There we go. Yeah. In that kind of white square. This is an area in the local elevation or in the local topography for this region that's relatively higher compared to these troughs. And so in these regions, we can calculate the power spectral density as a function of kind of roughness amplitude and orientation. Okay, so that's what I'm showing here. And what we find is that in areas outside of the troughs, roughness is relatively isotropic. In areas of subglacial lakes, this roughness decreases, which is something we'd expect for a more specular reflector. And then in areas, the troughs, the roughness becomes anisotropic. So all of the power becomes concentrated at a very specific azimuth orientation. And this is consistent with megascale glacial lineations. And so the ingredients that you need to have to form these kinds of bed forms include water, sediment transport, but also fast flow. So these are simulations showing kind of bed form morphology as a function of flow speed. And in order to get lineations, you need active sliding at a bed that's thawed, which is not necessarily what you might conclude given the surface expression of this interior dome region. So our observations are some of the first observations of lineated bed forms in an area of slow flow, but we can, lineated bed forms are common in other deglaciated environments. So this is 2 bathymetric surveys that were collected and analyzed by Julia Wellner and John Anderson, both while they were at Rice University. The bed forms an expression of the lineations for other environments that are deglaciated. This is multi-beam bathymetry in the Ross, have been used to understand the kind of death mask of a retreating ice sheet. So how do ice sheets that, after the glaciation, how do these systems evolve or retreat to their current configuration? And at Hercules Dome, we can do something a little bit similar, I argue, which is to understand the last time ice flowed quickly through this region. So it's the time period right before the ice sheet stagnated as part of ice sheet nucleation or re-advance. Okay. If we look at kind of where the troughs would route flow according to the bed topography, they align with larger fault-bound sediment basins that have been identified previously by Kate Winters and other folks at the British Antarctic Survey. And as part of the polar gap surveys, some of the aerogeophysical data that were collected include gravity data. If we do gravity inversions for what the density character beneath these paleo ice streams, what's the substrate beneath these systems, we find that in order to match the gravity data, we need low density sediments in this region where currently, again, the flow is very slow. So I'm going to just kind of leave it there and talk a little bit about kind of what we've learned, summarize. We find evidence of alpine valley landscapes, and these landforms are only revealed by conducting kind of these swath surveys using multi-element arrays. The formation mechanisms for the lineations and valleys is kind of inconsistent with the modern flow field. So I didn't talk about this too much, but the surface slopes at Hercules Dome are actually orthogonal to the orientation of this axis. And so this is a we're preserving in this landscape a very different flow configuration than the one we observe at present. And these lineations and valleys are kind of consistent, and then the presence of sediment as well are consistent with an ice sheet that's potentially very responsive in this interior region. So one of the active areas of research that my group is thinking about is improving on these methods for mapping using swath multi-element arrays, the bed topography, and in particular, thinking about how we can improve the cross-track width and then also the cross-track resolution of these images. So here I'm showing a figure that'll be familiar to some folks who've been involved in Coldex. I've been mostly involved in just supporting some of the processing for the multi-element data that were flown as part of Coldex. Shown here is the Basler aircraft, where we integrate actually 88 antenna elements in total in the belly of a Basler. And using this, this larger antenna array, we can map the cross-track bed topography in unprecedented resolution. So this is a profile of, again, the nadir-focused image as a function of distance and two-way travel time. But in the cross-track image there, I'm showing kind of the evolution of a surface reflection, but then also a bed reflection here as a function of this along track distance. And this profile was flown over White Island, which is very close to McMurdo and is part of the same volcanic province as Erebus. So it's the southern part of that province. And what we find is evidence of volcanic landforms in this topography. So shown here are some cinder cones that we've identified, a tuff ring, and then halioclastite ridges. And the morphology of these systems, which couldn't be revealed by just a nadir-focused or nadir-looking radar system, reveal information about the orientation of these structures. All these landforms are consistent with kind of explosive eruptions, and they're kind of the elongation of the axis of the cinder cones and then the halioclastite ridges is the same as the axis of the actual island itself. They kind of everything is self-consistent with what we would imagine for kind of the eruptive behavior of a shield volcano. And these combined with kind of samples from the rock repository can be used to understand both the geochemical history, but also kind of the landscape evolution of a system that's currently ice covered. So all of this information would be hidden without this radar system. So I'm excited to think about these processes with more folks and to potentially use the same system to uncover or reveal the bed topography of beneath other ice-covered ice caps in Iceland and other parts of West Antarctica. So I'm now going to talk about how we can use these multi-element arrays in other processing workflows. And we'll start by turning to multi-pass interferometry. Before I talk about the radar methodology, though, I'm going to walk through essentially how we can use radars or how radars themselves can manifest in kind of as signatures of flow behavior. So here I'm showing a simulation of a 2D ice sheet. In white are areas where the ice is currently flowing relatively slowly, and in blue, closer to the grounding zone, ice is speeding up. This ice sheet critically is in steady state with its climate forcing. And so you'll notice, right, that there's no change in the grounding zone position for this ice sheet. And then the surface here, the ice sheet, it remains constant. So what this means is that the surface mass balance, if you integrate across this domain, is going to be equal to the kind of the flux through this calving front geometry. And then plotted on these colors, which has now been infected with the flow, are isochronal tracers. And so each of these dots themselves is connected by lines that are consistent with our interpretation of conductivity contrasts that create the layer structure within an ice sheet. And there's a couple of different key features that I want to highlight that we can learn from these kind of simulations. In the interior divide location, you'll notice that our tracers pretty much deposit at the surface follow vertical trajectories. So they just move or are advected vertically with the flow while at the margins, the layer trajectories follow, or the tracer trajectories follow the layers themselves. So this is really critical for interpreting measurements of apparent layer deflection. And I'll talk a little bit about this more when I introduce another measurement. But for the multipass measurement, that's going to be the focus of the new work that I'm talking about. Critically, if we're profiling these layers and then trying to measure really subtle changes in the layering, that represents an Eulerian measurement. So we're not moving with the flow. We're actually taking a profile that looks something like this, waiting some time, and then letting layers advect, and then taking another snapshot and trying to measure or understand deformation. Okay, so a lot of this work is done from some of the same folks in collaboration with Nick, John Payton, and Knut Christensen. We're processing the complete archive recorded in Operation Icebridge, or collected by Operation Icebridge across Greenland. So for the two examples I'm going to talk about today, I'm going to focus on data that were collected at Summit Station here, and then Camp Century, which is over here. And yeah, but before I kind of get into those examples, I'll talk a little bit about kind of the measurement itself and then the radar processing. So as part of a first pass for just a radar system on an ice sheet, this is a schematic of the measurement itself. So as part of a first pass, we can collect data along track. We can then wait some time later. The layers themselves would vect with the flow. The surface will change with accumulation that we add top of our ice sheet, and we can take a second pass. And so critical for the kind of interference of these two measurements, we don't necessarily require that these passes are aligned. We wouldn't expect them to be aligned with one another. And so there's two really important corrections we have to make. One is to correct for the spatial baseline, so offsets in the vertical position of our antenna system, and then also kind of horizontal changes in the antenna system that can create offsets that are artifacts associated with layer slopes. Okay, so we have to make two important corrections for layer geometry and the position of our radar system that allow us then to isolate real deflection or change in the geometry of the layers themselves. So here I'm going to kind of walk through the processing steps. If we collect two profiles, we can equalize those two radar passes. We can then interfere those data with one another and build plots of phase change. So this is the apparent change in phase that we see beneath our radar system. We can then use the across-track geometry of the layer slopes to correct for the geometry of the layers. And when we include that information, the phase, we get a different answer than we did previously. And then we can calculate using the center frequency of that system what the displacement rate as a function of depth looks like. And this can be used to, again, calculate the strain rates. Okay, so this is the processing workflow that I'm going to show for two different case studies. Shown here, though, is all of the available Operation Icebridge data that we can use for multi-pass interferometry. So in white are all of the places where we have repeat passes, and in purple are the areas where we have passes where the spatial baseline between the passes is less than 100 meters, and at least one of the passes was collected using a multi-element array. So this allows us to correct again for the across-track geometry. And the first example that I'm going to talk about is a place where we have validation data. So if you remember from kind of the schematic and the flow animation that I made, in the interior region of the ice sheet, the Lagrangian and Eulerian measurement are actually very similar because our Lagrangian measurement of phase change isn't, the radar system isn't moving horizontally. So we put a PRES system at the surface, so that's what's shown here. This is another phase-sensitive radar system that can be used to measure deformation as a function of depth. We can make the comparison directly with the Eulerian measurement. So these data were collected by Fabian and other folks at the British Antarctic Survey to understand or quantify whether the divide has migrated or not. And we can use these data to understand the sensitivity of our measurement and also whether these two measurements agree. And we find that they do. And so there's, so red markers here are the PRES sites, and then these blue markers as part of the PRES survey are where we're comparing the multipass data here, shown in purple, with the gray P-res curves. So we find good agreement at locations near the divide. Near the margins, however, we can't make the same comparison with P-res because the Lagrangian measurement itself represents something different than the pulsed radar system in this Eulerian measurement. So here on the left, I'm showing a plot of coherence, which is just the measure of the quality of the interferogram and the interference between the two different passes. On the right here, I'm showing apparent phase change associated with these repeat passes. And then down here, I'm showing, again, this vertical strain rates that we get by averaging this apparent phase change, unwrapping the phase, and then calculating what that displacement looks like as a function of depth using the center frequency of the radar system. What we find is that on the Stoss side of a ridge in topography, we see that there's vertical extension in the ice column. And then on the lee side of that bump and ridge, we get compression of the layers. And that overall, we see net compression across the profile. And this behavior is consistent with what we know from kind of flow over bumps and ridges in topography from full Stokes models. So here now shown a Stokes model, the contours in this figure represent isochrones. So this is representing the age structure now, these points. And then the colors represent the vertical velocity. So we see to flow over the bump, you need a vertical velocity that's positive, and then it becomes negative again on the Stoss side of the bump. And we see expressed here an increase in the driving stress with the surface slope on the Stoss side of the bump. So I'm going to kind of summarize again, like what we can learn using these methods. Multipass methods that I've described here are all publicly available via the Operation Icebridge and Open Polar Radar Toolbox. So the multipath methods have been validated at Summit Station, and then they're consistent with kind of what we understand about the flow at Camp Sentry. And the other thing I would highlight is that only a small fraction of the total multipass data have been processed for all of Greenland. And so there's a lot of opportunity here to include this measurement in our understanding of ice physics and actually formally assimilate these data into ice flow models. Okay, so the third part of my talk is now going to get into applications using polarimetric radar. Now these can be used to understand ice fabric. I'm going to first, though, review a little bit of information or give some background on what I mean when I say ice fabric. So like other kind of polygenetic materials like wood grain and graphite, ice shears very differently depending on the orientation of the applied stress. And this has everything to do with the crystal grain structure. So shown here is a unit cell, which is kind of the smallest divisible cell of an ice crystal. And what you can kind of see here is that if we kind of split or orientate the unit cell in different directions that are defined by the crystal lattice. So for each red sphere here, this is an oxygen atom, and then the hydrogen atoms are connected to those oxygen molecules. And if we oriented in this orientation, that you can see that there's fewer hydrogen bonds that you have to actually break in one orientation along the basal planes compared to the c-axis. So this is why we get this anisotropic behavior within ice. And so the scale of the unit cell is about 1 nanometer. And then if you have a bunch of unit cells that are all oriented in the same direction, they comprise a crystal. So crystal grain is shown here. These can be any size that's kind of, any number of crystal single unit cells can form one unified crystal grains, be kind of a couple nanometers to almost a meter, so that we can get really large crystal grains in the bottom of an ice sheet. And if you have a bunch of crystal grains that are all oriented in some general orientation, they comprise the fabric, which is the bulk orientation of the crystal grains. Those they are shown here. And the bulk orientation of the crystal grains critically affect the rheology of the ice. So this is an anisotropic flow law where I have strain rate here as a tensor, and the enhancement factor, which is another tensor that can relate the applied stress to the strain rate response. And because the crystal lattice itself is sensitive to changes in the strain rate, ice fabric evolves with the strain history of this system. And so typically when you ask ice flow modelers what they need to understand the rheology of ice better, they'll often cite temperature as a really important condition that we don't have great observations of englacial temperatures, but over the strain rates that we see on Earth and the englacial temperatures that we see on Earth, fabric is also a major source of enhancement, of flow enhancement or resistance within ice sheet models. Okay, so this is work that's being done in collaboration with folks here, Ben Keisling and also Ali Balter Kennedy, along with collaborators at the University of Copenhagen. And what we're trying to do is understand how the strain history itself can be using essentially information about the fabric orientation here. Can we understand the strain rates, modern strain rates, but also the strain rate history? Because this information is something that takes time to develop. So similar to the rheologic and anisotropic behavior in ice, ice is also, there's dielectric anisotropy in ice as well, and it kind of relates to the same observable. So along the c-axis, ice or the propagating wave is 1% slower than along the axis of the basal plane. So if you transmit a radar pulse in ice, it'll propagate slower along the c-axis. And you can use that change in travel time with the polarimetric radar system to understand fabric anisotropy. So I'm going to appeal to this old schematic that I showed earlier. And if we change the orientation of our pulse and polarize it in different orientations relative to the direction of travel, we can then measure changes in the phase between those pulses and use that to understand the variance of the c-axis distribution projected onto the axis of travel. Okay, so here I'm going to kind of, again, walk through the processing workflow. We have two co-registered passes. This pass is being driven. They're driven at the same time, but again, we're very, very quickly alternating or going between two different pulse sequences. So we're measuring HH and VV. These, I should go back. The H pulse is just one orientation, one of those orthogonal orientations, and then the V represents the other orthogonal orientation. So we can, when we're talking about quad polarimetric radar, we're measuring transmit pulses in one orientation, H, and then receive pulses in H or V to then create a combination of four waveforms, HH, VV, HV, and VH. And this is hence why we call it quad polarimetric data. So here I'm showing an HH profile and then a VV profile. And if we, these are complex data. So if we interpret them in trace phase space, we can take the complex conjugate of the two copolarized traces and then average in the along track and use multi-look algorithms to correct for speckle and noise in these data, and then generate interference patterns or interferograms, this time of the wrapped phase difference between the HH profile and the VV profile. So these data are shown here for data that were collected in Northeast Greenland. And the important thing to kind of remember when you're interpreting these data is that more fringes means there's a stronger horizontal fabric. So I'm now going to turn to a couple different examples. The first is going to feature some work that Ginny did back in her PhD. So these were radar data that were collected and used to understand the configuration and flow speed and flow stagnation of the CAM ice stream. So CAM is located between Seiple Dome here and Engelhart Ice Ridge, and disturbances in the layers and then crevasses in the layers that appeared as kind of these specular or rather point reflectors that were buried by snow were used to date or create a hypothesis for when the ice stream may have shut down sometime in the past. So at some time, CAM ice stream was flowing very quickly. We can infer this from the layering structure. And around 250 years ago, it shut down. And using kind of a different data set, these are, again, using just the phase information between copolarized quad polarimetric data, collected near waste divide, but going in a long track approximately along a flow line down the central trunk of CAM, we find evidence of the same process occurring. So in the near surface, what we see is that there are very few fringes that are being wrapped together. And then as a function of depth, you get more fringes and evidence of kind of a stronger fabric that's relic at this time period when CAM ice stream may have flowed more quickly. And now turn to another example. This is also in West Antarctica. This is from the Thwaites Glacier shear margin. And we see, across this margin, ice is flowing kind of grid southwest. Across this margin, we see in the ice stream itself, lots of fringes indicating a very, very strong fabric. But outside of the margin, kind of a weaker fabric structure. And this interferogram is actually more difficult to interpret because we're not actually driving a long flow. So ice here has experienced two different strain histories. So we can't make the same kind of inference of ice stream shear margin migration maybe that we kind of did with the CAM system. But we can use other radar systems to kind of inform our interpretation of this margin. So now I'm showing in the first animation, the long track radargram that was collected with a swath capable radar system. So this is appealing again to the multi-element array. We're able to then localize across track kind of direction of arrival of the reflectors as a function of depth. And then here in the bottom, I'm showing kind of marching along the same interferogram as before. I've also included, though, some more data from inside the shear margin. This was collected with our quad polarimetric system. Shown here is the unwrapped phase. So the slope of this unwrapped phase can be used to understand the strength of the horizontal fabric itself. And what we find is that as we move into the shear margin, inside the streaming flow, reflectors are specular. Once we move into the shear margin, that was a turn there that caused most of the ambiguity in the across track. But we get a persistent reflector off axis. And this is right at the shear margin, right at this area where we kind of lose coherent reflectors in our quad polarimetric data, but where we can see something interesting happening here, I argue. So there's a diffuse reflector here that I think is emblematic of a change in fabric that's really dramatic and happens over a really narrow depth range. So here we see I'm here showing just the copolarized SAR focus radargram for an HH profile. And then in panel A is just zooming in at this top part of the surface to show kind of the layer resolution that we get. We're resolving layers here that are kind of 40 centimeters in scale. So this is the center frequency for this radar system is 750 megahertz. So it's really, really fine resolution and it's broadband, which is what allows us to resolve all these features so carefully. But at depth, we see a diffuse scatterer here. So the layering changes as a function of depth, and it actually cross-cuts some of the layers. And there's no real easy way to do that with conductivity contrast. So if you have layers that are just deposited snow at the surface, you can't really get a feature like this bisecting those layers. And so it has to kind of evolve or happen from a different mechanism. And I think this can help us understand the rheology in this system as well. So like if you have a fabric that's developing really quickly as a function of depth, it might be indicative of a change in the deformation mechanism. So we might be moving from something where it's instead of like a grain boundary sliding model for the rheology, we might be moving towards something like dynamic recrystallization. So this has kind of impacts for how we might parameterize the rheology for this ice stream system. Okay, so this is just a summary then of kind of what we can learn from quad polarimetric data. I think there's a lot. I talked a little bit with folks over the last 2 days about data that are being collected from Thwaites Glacier using a quad polarimetric helicopter system. And I'd be really excited to share some of our data potentially as a comparison with some of these observations that are being collected independently. Again, all the processing that I've described here is kind of publicly available as part of the Open Polar Radar Toolbox. And we find again that quad polarimetric radar data and signals that they shed light on related to the fabric can be used to understand current flow conditions but also when interpreted with other observations or like inferences of changes in flow for time, they can be used to understand paleo ice stream behavior. So again, this is just a summary of kind of all of the results, and the key takeaways that the new observations that are enabled by the new radar technologies and methodologies that are presented here can lead to new breakthroughs in our science. And so looking to the future, one of the kind of next projects I'm really excited about and potentially working, I'd be excited to include more folks from UT working on this, is using rover systems to create coordinated surveys that can tow and integrate these multi-element array technologies to answer or address different survey questions. One of those questions or applications that I'm really excited about is to perform autonomous common midpoint surveys, where we move out and spread out from a standard kind of mean spacing where we're then transmitting and receiving pulse information that can be used to separate intrinsic reflectivities at this common midpoint from path-dependent effects associated with vertical orientation of the crystal fabric and also interference effects from the layers themselves. So I've purchased 2 of these systems, and they're shown here. And so they're quite robust. You can, I think they're applications for other kind of field-related activities. You can take them up a volcano. They work very well in the snow. There's folks, the company that makes these, they're all retired snowmobile engineers working in Montreal. And they've used these essentially as like means to transport their ice fishing huts. And so they've been great to work with, and together we're building autonomy capabilities within these systems. So how can we use these to then program swath surveys where we're not just kind of connected with a rigid antenna element, but using multiple antenna elements that can be separated from one another. So I'm really excited about rovers. I'm also really excited to move to Texas, where there's also lots of folks that are thinking about ice sheets and then the impacts for coastal communities kind of locally and then further afield. And so I think there's great potential building on some of the meetings that Jenny's already started across groups with folks at the University of Houston, like Julia Wellner, to kind of create a space where folks across the Texas, the American Southwest, and the South can meet and talk about their sea level problems in an informal setting. With that, I'll just thank everybody, and if you have any questions, happy to answer them.
Awesome. Thank you so much, Andrew. We will start with any questions from students.
Thank you so much. It was a really awesome talk. I learned a lot about radar glaciology. This might be a silly question, but I'm curious about what you just showed in part 3 in terms of the phase changes in the ice fabric. And I'm wondering, can you link that to what's happening in our past climate? Like what's the time, I guess, resonance with that layer change?
Yeah, that's a great question. So I'm gonna go to another example quickly. Oof. Less quickly than I would have liked. Okay, so I'm gonna so I think this example is kind of one where it's validated by other measurements independently. And so I think we're definitely in this phase where we're proving this method. We're proving that fabric is something that can preserve information about the memory of ice flow in some region. Recently, there was a paper about the shear margins of the Negus and how they may have changed as recently as 2,000 years ago. This argument was constructed from layer chronology that was then dated or related to a depth age scale at an ice core site. And so I think there's, before we kind of get to inferences of fabric change more generally, there's a lot of work to be done in environments like Negus and for other systems where we have independent evidence that corroborates the information that we might learn from fabric. But crucially, I guess there's fabric is because it's a function of this flow behavior integrated over time. For a lot of these interior sites, we don't necessarily know the climate forcing that we should apply at, as a surface mass balance condition. We also don't necessarily know the downstream flux condition. And so I think these kinds of observations are something that we can use to test or invalidate hypotheses for past flow. I think that's kind of where it sits at present. But there are models that are being developed for fabric where we could formally like assimilate that fabric information in the model, use it to test maybe null hypotheses. But if you integrate over a long enough period of time, like say you just run your simulation for 1,000 years, you can actually use methods that folks like Patrick Heimbach here at UT have used to understand or evaluate kind of the sensitivity of the change in fabric to the flow behavior and say something actually about like a reconstruction of the flow for that region. Does that make sense? This is the I guess I didn't get to the fun part, but this is the fabric change that we observe at Negus at the shear margin of the eastern part of upstream Negus, and we see strong fabric in the near surface, and then in contrast maybe to the cam profile, weak fabric as a function of depth. And then this thing is a basal unit, and I don't know how to interpret that. Yeah.
Other questions?
Cool talk, thank you. So it's still we don't have the throwable. Try and throw. So I'm curious. One of the things you talked about in sort of future work was this idea of the common midpoint surveys, with the idea that you could get at intrinsic reflectivity. So I guess I'm curious if you could expand a little bit. I'm thinking about from the point of view of like reflection seismology, that tells you about physical properties and allows you to get at elastic moduli. Obviously, that's not the case here, but what is it that would get you in terms of constraining, say, the models that might predict the dielectric constants in their anisotropy? Or is there a way to connect that observation to something
physical,
important
yes.
and physical? Yeah.
So temperature structure is like the main goal of that measurement. So temperature structure and the orientation of the vertical fabric. So all of the fabric measurements that we're making are actually the horizontal component of the 3D fabric tensor, because we're actually transmitting and receiving from the same location using antennas that are polarized, but polarized parallel to the surface. So we can't really see anything that's oriented in some upward direction. That should be the strongest component of the fabric, but we don't know. We can't measure it. And so if you move out from a common midpoint, you can begin to sample the vertical component of the fabric, which I think is one of the reasons why common midpoint surveys have a difficult time just inferring temperature when you're using or relating intrinsic reflectivity to the models for how that affects the temperature. Does that answer your question? Yeah.
Yeah, great talk, Andrew. So going back to the Herc Dome work with the megascale lineations, have any insight into the evolution of the thermal state in that area? Is it frozen right now? Or has it melted in the past? Or
Yeah, this is a great question. I think in some regions it be faster just to we'll try to do this. Yeah, so at Hercules Dome, the thickness varies a lot as a function of a long track profile. So depending on where we are in the survey, oh my goodness, too many slides here.
the very first line.
Yeah. Yeah, so let's look at a summary slide like the one that's shown here. Okay, so we have topography varying by like 2,000, I mean, not 2,000, but about 1,000 kilometers across this grid. And so that is, that has impacts on how sensitive, right, like the basal thermal state is to the current surface mass balance and temperature forcing. So you can use simple kind of like Rapin temperature models for how temperature would be both advected, or I guess how temperature is conducted to the subsurface. And you can also advect temperature in. And so Ben Hills is a collaborator that we've worked really closely on thinking about this problem at Hercules Dome. And this is kind of as yet unpublished work, but there's evidence of subglacial lakes, particularly in the some of the deeper regions of the topography. And these are still consistent with modest geothermal fluxes in this region, which we don't know what that field looks like either. But if you're going to drill a core, you better not drill it in any place where there's a subglacial lake, and you better not drill it in areas where you actually want it to be pretty shallow, because there it's less sensitive to kind of the geothermal flux forcing, which could be high. And the fault-bound nature of some of these basins would suggest that it might be like spatially heterogeneous in a region that we're not going to capture or resolve with the current models for geothermal flux. Yeah, but we don't know, I think, and it's one of the reasons. I mean, it's a debated topic, I would say. I think the ice core glaciologists would really like it to be frozen everywhere in this region, and we don't see that.
I have a quick follow-up on that question. Thank you. Which is that, so you motivated this work with the polarimetry collapse scenario. Have you looked in a model or that model or any model about whether that collapse scenario gives you these flow characteristics that would erode these? Like, basically what I'm asking is this an ancient topography from the initiation of the ice sheet, or is this a signature of a collapse phase?
So we can't differentiate between the two. And that's like I guess the argument that we make in the paper is that between interglacial cycles, if the waste collapsed, that would be expressed similarly in the topography here compared to during ice glaciation. We haven't tested this. The one issue is that the resolution of some of this is an interior site, and most of like for instance, the Polarimetry model, I think it's like tens of kilometers that you're resolving. It would be like the average area of the kind of the finite element domain for this interior region. So we're not even going to capture any flow through a trough like this, which is small compared to kind of the resolution of the model. But I think it would be reason, or it could motivate a simulation where you maybe are trying to like focus on this interior using maybe like a nested domain or something like this. Yeah, exactly. Yeah. So
don't have that high resolution photography, you might not capture the event.
Yeah. Yeah. I think the larger point that we're I think the observations that we do have would suggest that this interior flow region, like we're either imaging the very beginning of ice sheet nucleation, which is like an observation that relates to something that happened like 30 million years ago, or we're seeing something that's happened more recently during interglacial cycles when we've had a collapsed configuration. But our evidence suggests that in both cases, this part of Antarctica, an interior region, where if you just did an inversion from surface observations using satellites, of the modern flow, you won't have any estimate of like the basal resistance here that would resolve or say that the bed here is weak or would promote flow or fast flow in a retreated configuration of the ice sheet. That makes sense. Yeah.
I'm just curious about this radar system and wondering, because you've used it in mostly inland areas, and we were having a conversation earlier about the need for radar in these like terminus regions, and they're wetter, more crevassed, much more challenging. You can't send a ROV across the ice surface. And so have you thought about like a way to get this on, like you have mounted it on an airplane before, is it capable of getting through thick, wet, crevassed ice?
Yeah, so there's been actually two different systems that I've talked about, and I've kind of avoided conversations maybe about the center frequency just to get through the content. But the multi-element array center frequency is much lower than the quad polarimetric system that we have at present. So one is probably better at deeper penetration. The lower frequency swath system would see deeper structure than the quad polarimetric system. And so if you're interested in Greenland outlet glaciers, I would suggest using the some kind of multi-element swath with like a center frequency of like 375 megahertz would be like, that's like a perfect system for that kind of, and it relates to maybe some of the newer systems like developed by Copri in collaboration with Alabama. They have a system that's kind of like really well tuned at kind of balancing some of these measurements and integrating all of these observations into one single platform. Yeah. Yeah. So if it is ground-based, yeah, this is a huge issue with if you're kind of dealing with sastrugi that are or sastruga that are like 2 meters size, really. So at Coldex, I think there were surveys that were part of the ground-based campaign at kind of Dome area that yeah were really challenging, I think, for folks to do heroic efforts to collect data with the system there.
Wonderful. So if folks have more questions for Andrew, which I know I do, please do join us this afternoon at ABW for happy hour. We'll be there around 4:30. Any students or postdocs that are interested in having lunch with Andrew, Casey's organizing a group to leave in 15 minutes from the main lobby. And oh, if you didn't get a chance to sign up on Andrew's schedule and you would like to connect with him more, I know Andrew is actually planning to be around next week, Thursday. He's visiting Rice as he prepares to move here in a couple of months. And so if you want to have a longer conversation, you can reach out to Andrew about potentially connecting when he's back in town next week. And with that, let's thank Dr. Hoffman once again. Thank you so much.